Last time we have introduced this graph, so you can imagine if the phi is 0 degree, you can only observe one peak here, which means the wavelength or the frequency doesn't change of the input X-ray doesn't change. And if phi is 45 degree, then there are two peaks, but they are not separate far away. They are quite close to each other. So you can see the delta lambda is somehow like this, 1 or 2 picometer. If it is 90 degree, or the wavelength difference is a bit larger. So close to 5 picometer. If it is 135 degree, yeah, the lambda difference is even larger. Yeah, this is not 5. This is 2.5. This is 70. This is 75. So this is 72.5. So this from this to this point is around 2.5. So for this one to this one is close to 5, a bit less than maybe 4 point something. Okay, so we try to explain this phenomenon using the concept of momentum, 动量. So here, suppose we have an electron, which is relatively stationary here, and then we have an X-ray with a wavelength lambda injected here. So if phi is 0, it's somehow like no energy is transferred to the electron. So nothing happened. It's just like nothing happened. But for this one, if this angle is phi, this angle is theta, which means that the X-ray go to this way, and the electron go to that way. So originally, if you regard this X-ray is a particle, have some property of particles, so it should have some momentum. And then after they collide, the X-ray have a final momentum, and the electron start to move will also have momentum. So the momentum should be conservative. Okay, so we can using the conservation of momentum, we can write a formula to do some calculation. Or in this case, if the phi is 180 degree, which means that this angle, this is phi. So actually this X-ray is directly reflect, going this way and then go back. So this phi is 180 degree, and which means that the electron should go this way. So here actually we can write one of the equation like this. So F is the original frequency of the X-ray. So E equals HF is the total energy, is the energy of the photon. And then F prime means after the collision, the frequency or the wavelength of the X-ray has changed to F prime or lambda prime. So HF prime is the final energy of the photon. and K is the kinetic energy of the electron. So we have some sort of conservation of energy because 这个是什么完全弹性碰撞啊，所以它能量还是守恒的。So we have some sort of conservation of energy here. So actually, we can make some variable substitution. And according to last chapter, the relativity, we know that the kinetic energy is lambda minus 1 multiplied by mc square, and yeah, we can actually derive an equation like this. Yeah, they can derive an equation like this, h over lambda, because c is f lambda, so we can just eliminate f and f prime by substituting f equals to c over lambda, and h equals to and f prime equals to c over lambda prime. So all the c can be cancelled. So we have only one c here. Although actually, I don't think we need this one to really calculate this equation. This is the final conclusion. Actually, using the conservation of momentum, we can write these two equations. For x-axis, this is h over lambda. So originally x-axis which is h lambda, and for this one, this is h over lambda prime times cosine phi, and for the y-axis, it should be somehow like h over lambda prime times sine theta, because this one is sine theta, this is sine phi, this is cosine phi. This should be h over lambda prime, So it is separate into x-axis component and y-axis component, like what you do in mechanics class. So for the electron, the momentum is gamma mv, if you still remember. So for x-axis, this one is gamma mv. So if you decompose it in x-axis component, this is theta, which means that we multiply by cosine theta here, and then we multiply by sine theta, but with a negative sign, because this is the positive y-axis. So this one we should have a negative sign. Actually, we can using these two to derive this one. So I try to show it. Okay, so actually we have like this. Yeah. So actually we can just move this term to the left side, and move this term to the left side. So we have gamma mv cosine theta equals h lambda minus h over lambda prime cosine phi. So using the first one, we can get this. We just rearrange the term, and then for the second one, we can also do the similar thing. Equals h over lambda prime sine phi. So our target is to show delta lambda equals lambda prime minus lambda equals to h over mc times 1 minus cosine phi, which means that we need to eliminate cosine theta and sine theta. So the most wonderful formula for the trigonometry function is actually sine theta squared plus cosine theta squared equals to 1. This is the most useful one, most useful formula. So actually we can just square this one. Square on both sides, square on both sides. And then we add them together. Okay, we add them together. So for the left side, we have a gamma square mv square cosine theta square. And then we also have gamma square m square v square sine theta square. So sine square plus cosine square will be 1. So on the left side, we have a gamma square m square v square. And then for this one, we should have 3 terms, a minus b squared, all squared. So we should be a squared minus 2ab plus b squared. So it should be like x squared over lambda squared minus 2x squared lambda prime, and then cosine phi. So this is minus 2ab. And then we have a b squared, which is x squared over lambda prime square cosine phi square. So this is the first one. And then this one, which is simple, which should be x squared over lambda prime square sine phi square. Right. Also, we have, let me see. Gamma MC. So also we have this one. H over lambda equals h over lambda prime, gamma minus 1 MC. So we try to move it there. H over lambda equals h over lambda prime plus gamma minus 1 mc. So actually we can also rearrange the term. So this is gamma mc minus mc. And then we can move these two to the left side, or just exchange. So we have a gamma mc equals h over lambda minus h over lambda prime plus mc. Slightly rearrange the term, we'll come up with this one. And similarly, we can just square both sides. Okay, square both sides. So on the left side, we have gamma m square c square. And then on the right side, it will be a bit more complicated. It is somehow like a plus b plus c square, which would be a square plus b square plus c square plus 2ab plus 2bc plus 2ca. right? So we should have x squared over lambda squared minus plus h squared over lambda prime squared plus m squared c squared. And then we should 2ab, 2bc, 2ca. So we should be like 2h squared over this should be minus sign because this one is negative. So this one should be minus lambda prime. So 2ab, and then 2bc should be still negative, minus 2h mc over lambda prime, and then 2ca should be plus 2h mc over lambda. So actually we have this one we can call, this one we can call A, this one we can call B, and we can have B minus A. So for B minus A, for the left side, we have gamma square m square, gamma square m square. So it becomes gamma square m square c square minus v square. And then we can see that this one and this one can be cancelled. This one and then we will have this one is m square c square, and then the next one is this one minus this one. So this should be plus not this one. It should be this one. It should be like 2h squared over lambda prime. So minus this term, so this should be positive. So it's like 1 minus cosine phi minus 1, cosine phi minus 1, cosine phi minus 1, because here we have cosine phi. This is multiplied by 1. So this term is here. This term is this term. Okay. So we should still have these two is 2h mc and then lambda minus 1 minus lambda prime minus 1. 1 over lambda prime. 1 over lambda prime minus 1 over lambda. 1 over lambda minus 1 over lambda prime. And And actually we can see these two term we have cosine square phi and then sine square phi. So these two terms should be x squared over lambda prime squared, and then which means that this term and this term can be cancelled. So actually we have we have this one, we have this equation, and then the next step is, if you still remember, gamma is 1 over square root of 1 minus beta squared. So actually it's somehow like this, 1 minus v squared c squared, which should be c squared minus v squared, and then on the top is c squared. So we have a lambda square like this. So we can substitute here, c squared over minus v squared times m squared c squared minus v squared. So this one and this one can be cancelled, and finally it becomes m squared c squared. So on for the left side, which means that these mc square and mc square can also be cancelled. So they can be cancelled. And then finally we can further rearrange the terms. It is somehow like this term is 2hmc, and then we have lambda prime minus lambda over lambda prime. So we just subtract these two terms, so it becomes this one, and then we move this one to the left side and put it here. So it becomes 2h squared over lambda prime 1 minus cosine phi. So finally we can eliminate these 2h. So finally we get the answer. The answer should be delta lambda equals lambda prime minus lambda, and then we subtract this on both, not subtract this, divide it on both sides, divide mc. So mc and mc cancel. So finally here should be this one, h over mc. We have h over mc, and then multiply by 1 minus cosine phi. So this is the final equation we will want to prove. Any questions? So actually we prove this one, and actually this term h over mc is called the Compton wavelength. It has some specific physical meaning here. Yeah, because it's somehow like when there is some incident wave, and let me see. Okay, when there is some incident wave, And this means that cosine phi should be 0. Cosine phi should be 0 means phi equals 90 degree. Phi equals 90 degree. When phi equals 90 degree, delta lambda equals h over mc. So which means that this is the wavelength change to the X-ray when the departure angle is 90 degree. Departure angle is 90 degree. So this is actually not a wavelength. This is actually not a wavelength. This is a wavelength difference for the X-ray. But for this phenomenon, we need to use the momentum to really explain it, or energy and the momentum, which is some property about particles to really explain it. So here's an example problem. So X-ray of wavelength lambda equals 22 picometer, photon energy 56 kilo eV are scattered from a carbon target. The scatter ray are detected at 85 degree to the incident beam. What is the quantum shift of the scatter wave? So actually we only need to use that equation. So, and then h is 6.63 times 10 to minus 34, and then the mass of a electron is 9.11 times 10 to minus 31, and then C is 2.998 times 10 to the 8th power, and then 1 minus cosine 85 degree. So it would be 2.2 picometer. So we just use this equation and substitute the number into it. And then for part B, what is the percentage of the initial X-ray photon energy is transferred to the electron in such scattering? So actually we can calculate it by F fraction. Originally it should be HF, the original energy of the X-ray, and then the final energy of the X-ray should be HF prime, and then all the energy should be transferred to the electron as the kinetic energy. So we divide it by HF because we need to somehow calculate the portion, the percentage of the energy. So HF is actually HC over lambda minus HC over lambda prime, and then here we have a C over HC over lambda here. So all the H and C can be cancelled. All the H and C can be cancelled. So it is somehow like lambda prime minus lambda, which is delta lambda minus lambda prime. So in the previous one, we know that delta lambda is 2.2. So 2.2, and then lambda prime. We know that it is lambda delta lambda is lambda prime minus lambda, which means that lambda prime is delta lambda plus lambda. And then the original lambda is 22. So it's 22 plus 2.2. Or in the other way, you can imagine the energy becomes smaller, which means that the wavelength should be longer. The longer the wavelength, the lower the energy of the photon. So it is maybe you can multiply it by 100%. So this is 9.1%.